Thank you so much for that very kind introduction, Martin. And it's, I have mixed feelings about giving this lecture as my very last one as Gresham Professor. I've had such a wonderful time, and I'm so grateful to everyone who's supported me in this role. So in this, then, my final Gresham lecture, I want to talk about one of the defining characteristics of mathematics, and that's proof. So if we imagine ourselves 2,000 years ago in ancient Greece, as we're all well-educated people, we all know that there are 4 elements that make up everything in the universe: earth, air, fire, and water. And we also all know that if you have a right-angled triangle, the square on the hypotenuse is the sum of the squares on the other 2 sides. Now, today, we still believe one of those things, but probably we don't believe the other. And the difference is proof. We have proved Pythagoras' theorem mathematically. And when you have a mathematical proof, as long as it's correct, then what you've proved is true. And it's true now, and it'll stay true. So today, I'm going to show you some of my all-time favorite mathematical proofs. We're going to talk along the way about what makes a great mathematical proof, but everything I'll show you today has something in common, and that is a flash of pure genius that makes these things even more delightful. So I hope you'll enjoy them, and I thought we should start with, since we've already mentioned one theorem, proving Pythagoras' theorem. Now, there are lots and lots of different proofs. This theorem has been discovered and rediscovered in lots of different cultures over many different times. Many proofs, hundreds of them are out there. So it's hard to pick the favorite, but I've got 2 to show you because I couldn't pick. Let's just remind ourselves, we all know Pythagoras' theorem, but just to be sure, if you take any old right-angled triangle and its sides are a, b, and hypotenuse c, then we know that a squared plus b squared equals c squared. Okay, iconic equation. So we're going to take this triangle and we're going to look at 2 diagrams. And you almost don't need any words at this point. These 2 diagrams almost just tell their own story. So both of those show a big square. Its side is a plus b. And inside that square, we've got 4 copies of our triangle and then some space that's left. Now, on the left-hand side, the space that's left is a square of side C. In the right-hand side, once you've taken account of those 4 triangles, the space that's left is divided into 2 squares. One has side A, and one has side B. So because you've got the same area in each picture, those areas are the same, so we can straight away say that c squared plus 4 times the area of that little triangle is equal to a squared plus b squared plus 4 times the area of that triangle. And so those things are equal. So we get a squared plus b squared equals c squared. I think it's a very pretty little proof. I want to show you another proof, though, and this is not because we need to prove something twice. If our first proof is correct, that's fine. That's all we need. But often we see that if you look at things from a different viewpoint and prove things in a different way, it's fun, there's no problem with that, but also it can show you different approaches, maybe ways you might generalize what you're talking about, techniques you might use elsewhere. And the other proof of Pythagoras' theorem I'm going to show you, I really like it because, to me, it feels surprising that the outcome tells you something about the areas of squares, because it doesn't seem to involve any of those things along the way. So let's see it. Here's our triangle, our right-angled triangle, sides A, B, and C as before. And we're going to drop just a perpendicular from that top vertex. Like that. That divides our triangle into 2 smaller triangles. Now, each of those smaller triangles is similar to the one we started with. Similar as in all the angles match up. And just make sure we believe that. The one on the left, that green one, we can see the right angle there. We can see it's got that yellow angle, the same as the big triangle. Well, whatever's left, we know the yellow and red angles add up to 90 degrees because they're in the big triangle. So the remaining angle must be the same as this red one. And in the blue triangle on the right, same thing. We get now the red and yellow angles as before. So those 2 triangles are similar to the big one. And we know about similar triangles that ratios of lengths of corresponding sides are equal. So if we look at that big triangle, if we take the hypotenuse, length C, and the second longest side, A, C divided by A will equal that corresponding ratio in the left-hand triangle. So the hypotenuse of that one is A, and the next longest side is X. So we get C over A equals A over X. And we can do the same thing in the right-hand triangle, this time comparing the hypotenuse to the shortest side. So in the big triangle, C over B must be equal to, in the small triangle, B over Y. Okay, so we get these two expressions. Now, all we're going to do is tidy those up a bit. Get rid of the fractions, rearrange a little bit, and we see from these, we find an expression for A squared, it equals CX, and for B squared, on the right, that equals CY. Now, we want to know what's A squared plus B squared. So we can just add those up. A squared is CX, B squared is CY. Bring out that factor of C. Now, what's X plus Y? Oh, it's just C. X and Y is how we divided up that long bottom side, C. So again, we get this, it just falls out. Pythagoras' theorem, A squared plus B squared equals C squared. I really love this because, yeah, it's just a surprise to me. Nothing about areas really in here. We just do a couple of little calculations with similar triangles, and out comes the theorem in a completely different way from how we saw it before. So that's just beautiful. And there are hundreds of proofs of Pythagoras' theorem out there, so I encourage you to go and have a look and try and find your favorite proof of Pythagoras' theorem. Well, let's think then about what comprises a proof. Before you can do anything, before you can even write the word proof and begin what you're going to do, you need something that you want to prove. So Pythagoras' theorem tells us something about right-angled triangles, which had to first be noticed. So you look at lots of different right-angled triangles, and after a while you notice this relationship between the length of the sides. You spot a pattern, and you make a conjecture. And then, and only then, are you going to try and prove it. So in order to do any kind of proofs at all, we have to be good at making conjectures, and that's all about spotting patterns. So we're going to have a practice pattern spotting now. So here's a question. We've got to work out what the pattern is here. So you draw a circle. You draw some points on the circumference, n points. Let's say n equals 3 to begin with. And we're going to join those points with lines, like this. So n equals 3, join the points with lines. And the question is, into how many regions can we divide the circle by doing this? All right? So with 3 points, you can instantly see I've got 4 regions that I've divided that circle up into. So a bit early, perhaps, to make a conjecture. N equals 3 gives answer 4. We haven't got enough information. So let's get some more data. Here's some more data, okay? So the numbers here are how many regions we've managed to divide the circle into. With 1 point, just the circle itself, 1 region. 2 points, we've divided that region up into 2, so we've got 2 regions. 3 points gives you 4. 4 points, you can eyeball that and see it's 8. 5 points, you might not necessarily instantly count that in your head, but let's count it. 1, 2, 3, 4, 5, 6, 7, 8, let's see, 9, 10, 11, and then that last bit, 12, 13, 14, 15, and 16. Okay, so look at that pattern. 1, 2, 4, 8, 16. We are in a position to make a conjecture, right? This is like, oh, powers of 2. But if we want to prove this, you sort of think, well, how? Okay, the number of regions seems to be doubling whenever I add a point and all of the lines that go with it. So somehow doing this is going to perhaps divide each region into 2. That's how we might double. But it seems really hard to do this calculation. And the way I counted those off there was a bit haphazard. It's hard to spot what's going on, the structure of what's going on. So if we don't know how to do our proof, perhaps we do the next one up and see if we can do it in a bit more of an organized way. So let's think what happens when we have 6 points. So I've sort of drawn them kind of haphazardly on this circle. And let's count in a more systematic way. So with 6 points here, we've got the regions on the outside. There's 6 of those, the ones with curved parts to them. And then we can kind of go back in the triangles next to those little regions there. There's 6 there, so 6 plus that, we're up to 12. And then we've got this kind of 6-pointed star, and the points each comprise 2 more regions, the ones I've coloured yellow, so we've got another 12 regions there, so 24 so far. And then we've got another 6 regions that I'm coloured in green here, so up to 30. And then there's only 1 region left, which rather messes up our lovely idea that we were going to prove powers of 2. Well, what's happening here? And I have to break it to you, it only gets worse. The next two numbers in this pattern are 57 and 99. Right, so we're getting further and further away from the powers of 2 that we thought. So what I was really doing here is saying, yes, we need to make conjectures and spot patterns, but we really, really, really need proofs. Proof means never having to say you're sorry. Right? We're not going to have to go back on our word. If we could prove, we can work out what this pattern is and prove it, get a formula and prove it, then we are going to know for sure what happens rather than having to make a guess, which might then later be wrong. So I'm going to leave to you, if you want to think about what on earth this might be and what's going on. In the transcript for the lecture, I have put what the formula is, and I've given a proof of what it is. So it's a bit long to do now, but if you're interested in that, you can look at that later. So this is my we need to prove things for sure. So then, once we've made a conjecture and we think we know what the right answer is, we want to prove it. We have to prove it. What is a good proof then? I'm saying the proofs I'm showing you are lovely and beautiful, and I can say that because I didn't think of them. You know, these are wonderful mathematical edifices passed down through the ages for us to all marvel at and be just enjoy for their loveliness. What is it that mathematicians rate about a proof? What do we think makes a good proof? Well, let me give you an example of something that will, first of all, not a good proof, and then we'll see how to make it good. And it's another possible pattern. So this one is about an expression. I'll call it f of n, and you work out n squared plus n plus 41. Okay? And we're working this out for numbers n starting at 0, so whole numbers, integers. So if you put n equals 0 into that, you just get the constant term, 41. So that's a prime number. If you put n equals 1, you get 43, also a prime number. N equals 2, 47, also a prime number. N equals 3, let's do it, is it 53? Also a prime number. You think, oh, gosh, lots of prime numbers coming out here. If you take this a bit further, the first few terms, you can see all of them are prime. It's prime for the first 10 values. It's prime for the first 20. It's prime for the first 30. You start thinking, oh, my goodness, I've got a prime number generator here. Well, since the incident of the circles, perhaps we don't necessarily believe that all of these numbers are going to be prime forever. And in fact, we'd be right to be skeptical. These are not always prime. So how could we prove that once we've discovered it? So what we might do, in fact, the first time we see a question like this, we might, and it's a perfectly legitimate thing to do, just keep plugging in values and just keep going and going and going. And eventually, this is the bad proof, after a very long time, and I'm not going to do it, but it wouldn't make for a great lecture, we get to the number 1,681, and we notice, oh, that's not prime. Oh, it's not prime. Right, we can stop. We found a value of n for which that is not prime. And so it would be a correct proof. It's just not a great proof. It doesn't really tell you anything. It doesn't have insight. You've just plugged away at it. So you can call this a proof by exhaustion, if you like. But a great proof of this is to notice something about what's going on. That 41, if we put n equals 41 into that expression, then every term, 41 is a constant at the end, everything with an n in, if you put n is 41, will now be divisible by 41. So every term will be divisible by 41. So we've got a multiple of 41 will come out, a bigger multiple than 1. And so that can't be a prime number. So that observation, once you've noticed that, means you don't have to do any calculations at all, which is always good, and you certainly don't have to do loads and loads of them. You just notice, of course, this can never be prime. And another great thing about this observation, which makes it a good proof, is that you can generalize it pretty much instantly. Because there was nothing special about the number 41 there, really, that enabled us to do this trick. So we can instantly generalize this and make our own little theorem that says actually no expression like this, but of this form, something like an squared plus bn plus c. No expression like that will always give you prime numbers for n greater than or equal to 0. And that proof will go something like this. If the number c, the constant term, is not a prime number, then you're already happy when n equals 0. Because when n equals 0, the output is c, not prime. Done. So we only need to worry about what happens when c is prime. But when c is prime, the trick I've just noticed instantly works. F of c will give you something that is not a prime number, because we will have a factor of that prime. So we're done. So it's an observation that, one, makes your proof extremely short, but two, we can generalize it and get a much more wider result. So that, for me, is the essence of what makes a good proof. It's elegant, it's short, it's ingenious, and it tells you something about what the situation. Okay, so I'm going to show you now 3 different proofs that use 3 ideas or concepts that are really ingenious, and they sort of lead us to techniques that we might be able to use more widely. And each of them I love for their different reasons. So the first one is about this question: how many different sums add up to n? So n, positive whole number like 3, and what I'm talking about, everything's a whole number here, and I'm counting as different. You'll notice 2 plus 1 I'm saying is different from 1 plus 2, so the order matters to me. If that doesn't matter to you, it's a different question with a different answer that you might think about separately. But in this case, just genuinely, what are the things in what order add up to 3? And there are 4 possibilities: 3, 2 plus 1, 1 plus 2, 1 plus 1 plus 1. Okay, so there's 4 sums that make 3. And there are 8 sums that make 4. You can check if you like. So is it powers of 2? Now, we're still a bit suspicious after the circles. In this case, though, it does turn out that it's powers of 2. But how on earth could we prove this? We're somehow thinking it's got to double. The number of sums has to double every time you go up by 1. So you might think, well, is there a way to make those sums that give you 3, I can turn those into sums that give you 4 by just adding 1 somewhere, but I've got to do it systematically. Maybe I just increase the first number by 1. That would work. All of those are sums that give you 4. 4, 3 plus 1, so the 3 becomes 4, 2 plus 1 becomes 3 plus 1, so on. That obviously isn't giving us everything. So is there something else we could do? Well, maybe we can add an extra term. We can add a 1 at the end. If we do that, then 3 becomes 3 plus 1, 2 plus 1 becomes 2 plus 1 plus 1, and so on. So now we've got 8 things, but unfortunately, we've got some duplicates, and we've got some missing sums. So this doesn't give us everything. Maybe there's more things we can do, but if you try and explore the possibilities here, it becomes so horrible and complicated and messy. It's really, really difficult to make progress if you take this approach. And so you might feel a bit stuck. And then, inspiration. There's a lovely, lovely argument that settles this and shows that, indeed, if you want to make the sums that add to n, there are 2 to the n minus 1 of them. So, for example, when n equals 4, n minus 1 is 3, 2 cubed is 8, that's the correct answer. And the little bit of genius that allows this to happen is this. It's turning this question into a different question with the same answer, which it's easier to calculate in that other context. So what you do is you take a string of 1s, n of them, just in a line with little gaps between them. So if you've got n 1s, how many gaps? N minus 1. Okay. In each of those gaps, we're going to put a symbol. We've got a choice of 2 symbols. We can do every possibility. So the first symbol we can use if we want is the plus sign, and the next one is a letter G. That seems a bit odd. G is going to stand for glue. That's why. Because if you've got 2 1s with a G between them, you are going to glue them together to make a bigger number. Here's an example. If you take 5 1s in a row, and where you have a G, you're going to glue those together. So you've got 1 glued to a 1, that makes 2. Then a plus sign, that means plus. Then 1 glued to 1 glued to 1, that makes 3. So we've coalesced into 2 plus 3. And we can see that actually every possible sum that makes, in this case 5, but in general n, you can arrive at by doing this process in exactly one way. It's a really kind of well-defined setup. So this allows us to translate that question about sums that make a number into saying, how many ways are there to put in n minus 1 spaces symbols where you've got 2 possibilities for each one? So plus or G, so there's 2 ways to fill the first space, times 2 for the second space, times 2, times 2, times 2, n minus 1 spaces, that's our answer. That's the number of ways to assign those symbols, 2 to the n minus 1, and therefore that's the number of sums. So that little flash of insight there that allows you to translate this question into something we can answer much more easily, that's the key to this beautifully simple argument, which I really love. Okay, next one. The principle here is so kind of self-evident that when I tell you it, you're going to think, that's ridiculous, that it's even got a name. But it's extremely useful, extremely, extremely useful. And it's this, it's called the pigeonhole principle. Because you imagine some pigeons, and they're going to each go to a pigeonhole, but if you've got more pigeons than pigeonholes, there's going to be at least one pigeonhole that has more than one pigeon in it. That's literally as easy as this is the whole principle, right? If you want to be more formally, if you have k boxes and n objects to put in them, if n, the number of objects, is bigger than k, the number of boxes, then we are guaranteed that at least one box will contain more than one object, however they arrange themselves. Maybe they all go in one box, or maybe they spread themselves out as widely as they can, like people sitting on a bus. But in this case, if there's more objects than boxes, we are guaranteed to have a box with at least two, more than one object in it. Okay, so this is used in so many proofs in mathematics, and many are, very beautiful, but would take a long time to give you the background behind. So I'm going to give you kind of a toy example. It's not particularly profound, but it's kind of fun. I picked a totally random number here, 42. You can this works for any number, any whole number. It says there's a multiple of 42, which consists just of zeros and ones. Now, okay, I'm not being clever, I'm not saying write it in binary. I mean genuinely writing in base 10 in our normal number system, we can guarantee that there will be a multiple of 42, or in fact any number, as we'll see, which just has ones and zeros in it. So lots of possible numbers out there of that form, but how do we go looking for these things, and how do we prove that this is always going to be possible? Well, the argument goes like this. Let's just think about numbers that only have ones. 1, 11, 111, and so on. So obviously you can carry on that sequence as far as you like. Those are going to be the things that are going in the boxes. Those are the objects that we're going to put into boxes. The boxes are going to be remainders. Take any number. If you divide it by 42, you get some quotient, don't care about that, and a remainder. The remainder is somewhere between 0 and 41. It can't be 42 or more, because otherwise we could take off another multiple. So when you divide by 42, there are exactly 42 possible remainders, from 0 to 41 inclusive. So we're going to take these numbers. We only need to go as far as the 43rd number. And at that point, we know, by the pigeonhole principle, we're putting those numbers into the boxes that go with the remainder. There must be at least two of these numbers somewhere in the sequence that have the same remainder when you divide by 42, because there are 43 numbers going into 42 possible boxes, which we label with the remainder. So it just must happen, pigeonhole principle. So we have these two numbers, at least two numbers. So we'll take the bigger one, there's the bigger one, there's the smaller one. They're both some multiple of 42, we don't care what, plus the same remainder r. So all we need to do now is subtract the smaller from the bigger. If you do that, you get some string of ones followed by a string of zeros, and that is going to be a multiple of 42, because the remainders cancel with each other. So this is just guaranteed to happen, which I think is very cool. And the 42-ness of this was not important at all. We could do this for any number n. Just take the first, I guess, n plus 1 numbers that are a sequence of ones, and then look at what happens when you divide by n, the remainder, there are n possible remainders, n plus 1 numbers to put in them. It's the exact same argument. So any positive integer n divides some number of this form, which I think is kind of cool and unexpected. There's no reason to think that that would be guaranteed. So that's quite fun. And the pigeonhole principle, yeah, really, really useful technique. Okay, the next idea is something that geometry proofs just really, really often do this kind of thing. So I'll show you a nice little theorem, which is perhaps not as well known as some of the other theorems in geometry that we may encounter, but it's very pretty. Viviani's theorem. So take an equilateral triangle, draw a point anywhere inside that triangle you like, anywhere at all. And if you work out the distances from that point to the sides of the triangle, the sum of those distances is always equal to the height of the triangle. So I think it's a lovely little fact. So let's see a proof of this. The first thing to notice, in this triangle, indeed in any triangle, the area of a triangle is half the base times the height. okay? So if the base, I'll just call the base B, the area is half base times height. Fine. Now, here's the trick. We're going to join some extra lines that weren't there in the question. This is, when you're trying to do geometry proofs yourself and you see one of these things, maybe your first instinct is to go, oh, why didn't they just put that line in already? But, once, it's okay. Like, we don't always, I may not have thought of this proof, and we may not have done, but we're just admiring the beautiful masterpieces here, without feeling annoyed that we didn't think of them. We just admire the loveliness. So let's admire the loveliness. Let's join some lines. We're going to join this point to all the vertices of the triangle, like that. That divides this triangle up into 3. So now we're going to just unfold the diagram. And we see we've now got these 3 triangles. All of them have the same base. It's an equilateral. The original triangle was equilateral, same base B. And so that total area is the sum of the areas of these 3. And of course, what is all of their areas? Half of the base times their height. So we get this. We've got half bx plus a half b z plus a half by. And if you just bring out the common factor, you can see instantly x plus y plus z equals h. So really, really nice little fact about equilateral triangles that I love. And the key to this was just drawing in those lines. So always look for lines that you can draw in. If it's a circle through, draw in a tangent, something like that. Okay, so this proof involved a diagram, because it's a proof, it's a result in geometry about triangles. You might expect a diagram. But diagrams and visual helps can be really useful in proofs that are not necessarily coming from geometry. So I'm going to show you a couple of those. And the first is probably better known than the second, but the one leads to the other. So the first one is about, we sometimes call these triangular numbers. It's basically when you add up the first few numbers, 1 plus 2 plus 3, and so on up to n. So you can think of this as making triangles and how many dots you need to make triangles of each size. So for the first one, it's like 1 dot. And then a 2 by 2 triangle, if I can call it that, you have to add another row, which has 2 dots in it, so 1 plus 2 gives you 3. Then for the triangle of kind of size 3, you have to add 3 more on the bottom. So 1 plus 2 plus 3, 6. And then for the fourth triangle number, I'm calling these T4, T5, and so on. We have 1 plus 2 plus 3 plus 4, which is 10. You can go on, 15, 21, 28, so on. So this is the number we're interested in, this quantity. Is there a formula for this? Adding the numbers from 1 to n, we'll call that Tn, the nth triangular number. Is there a formula that will save us some time? So it's sort of instinctively a bit lazy. We don't want to spend all day adding up laboriously the numbers all the way from 1 up to however big n is, 1 million, whatever it is. Well, okay, there is. Spoiler alert, there is. And the way to see what the formula is, one way, relies on pictures. So here is the nth triangular number. Well, in this case, n equals 6, but general. Here we go, all these dots piled up. So we've got this is n high and n dots along the bottom. And all we're going to do is just not change the number of dots at all. We're just going to, technical terms, scooch this along so that we've now created a right-angled triangle there. And the number of dots, I've just put each of them in a tiny little square. And what we're going to do is we're going to take that exact picture, copy it, turn it over, and join it on. So we're now going to get 2 of these things. And now what we've got we've got a rectangle. And the total number of dots in that is the area of that rectangle, which is its base times its height. And that is, well, n plus 1 is a bit obscured. Along the bottom, we've got n from the original triangle plus that 1 extra, and the height of this thing is our n. So the total area of this rectangle is just n times n plus 1. That's twice the number we need, because we use 2 copies of our triangle. So all we need to do to get the formula for the nth triangular number is just divide by 2. And this is the formula. So there's a lovely anecdote. It's unclear how much evidence there is that it really happened, but the great mathematician, Gauss, it's said when he was a small child at school, the teacher at the end of probably a long day, I imagine this teacher wanting just half an hour of peace. So he said to his pupils, okay, guys, you're all going to sit down, and I want you to add up all the numbers from 1 to 100, while I just sit quietly over here, mopping my brow. And then his lovely pupil, Gauss, immediately, sir, it's 5,050. because he had, the legend has it, worked out this formula and realized in order to add all the numbers from 1 to 100, that's n equals 100, you just have to do a half times 100 times 101. And so you can do that instantly, whereas adding them all up one by one takes you an awful long time and you probably make some mistakes. So I don't know if that's true, but it's a nice story. Okay, so this is the numbers, adding up just the numbers from 1 to n. Let's raise our game a little bit. Let's add the squares, the first n squares, 1 plus 4 plus 9 plus 16 and so on, up to n squared. I'll call that Sn for squares. What's that? Now, you may have seen, if you've seen that first proof with visual proof for the triangular numbers, you may have seen, I've certainly seen proofs of this, that involve fitting pyramids into cuboids. Now, for me, at that point, it kind of switches, and I find the algebraic proof of whatever this formula is going to turn out to be, I find the algebraic proof more easy and intuitive than fitting pyramids into cuboids. Maybe that's different for you, and of course, everyone has their own tastes in these things, but there is a visual proof that I find really helpful in seeing some of the connections with the triangular number formula. I'm going to show you that. I like it a lot. So here's a triangle, but instead of dots, we've now got numbers. So in the first row, it's 1s, and then 2s, 3s, 4s, and so on. And so what have we got in here? Well, the second row, 2 2s, that's 4. The third row, 3 3s, is 9. 4 4s is 16. So what we've got here is the sum of each row is that square number, and the sum of the numbers in the whole triangle is exactly the thing we're interested in, the sum of the first n squares. So if we could work out what the total of the numbers was in this triangle, that's the thing we're after. So you take that triangle, we're just going to knock it over to the right and to the left, get 2 more copies of it. So exactly the same numbers involved, we've just tipped them over. So each of these triangles, the sum of the entries is our Sn that we're interested in. Now what we're going to do is superimpose these triangles on top of each other. So we'll now kind of combine all of these 3 triangles, and we'll do that, the numbers, we're just going to add the numbers in each place together. And if you do that, now this might take a little bit of thinking, you might have to convince yourself of this. Every entry in this combined triangle is 2n plus 1. If I just add another little row in there, just on each one we can see. So if you look at the top corner there, n plus 1 plus n, that's 2n plus 1. Go down, we get n plus 1 plus 2 plus n, 2n plus 1. Hopefully you can convince yourselves that every entry in this combined triangle is 2n plus 1. So we can add all of those up if we know how many entries there are. How many 2n plus 1s have we got to add together? And if we do that, well, how many entries are there in each of these triangles? It's just the number of dots in a triangle of size n. So it's the nth triangular number. And if we do that, we've got these 3 triangles combined, so we've got 3 times the sum we're interested in. So we find that 3 times our Sn that we want is just equal to 2n plus 1 times the nth triangular number, which we just proved was half n plus 1. And so to get our Sn, we just divide everything by 3, right? And this is the formula we get. So if you've seen this formula before, you will know it's come out correct. For me, I saw this formula, and the way I was taught to prove it originally uses a technique, an algebraic technique called proof by induction, which we're not going to talk about today, but it's a very excellent proof technique. But it does not, that just doing it purely algebraically does not really explain why this formula is so clearly related to the formula for the triangular numbers. So I really love this proof because it gives an insight into what the connection is between them. So yeah, top marks for this proof for me. I really enjoy it. So we've seen these proofs, these 2 visual proofs. I'm going to go back to one that does not involve drawing a diagram, but it's one of the first oldest proofs that we have, dates back to Euclid, and it uses an amazing idea. We're going to prove that there are infinitely many prime numbers. And you may have seen this proof before, but I have to include it in a lecture of the best proofs of all time, right? It's kind of, you can't, I'd be thrown out of the Mathematicians Guild, which doesn't exist, if I didn't include this proof. It's so amazing, because it really, if you think, how on earth can you prove that something goes on forever? How is that? We can't do that. How can we do this? And it involves doing a little thought experiment. So here we go. Imagine this wasn't the case. Imagine that actually there's only a finite number of primes. Then you can imagine a list of them all, 2, 3, 5, 7, and so on up to whatever the highest prime number is, let's call it p. Now we're going to make a number. I'll call it n. You make it by multiplying all the prime numbers together and adding 1. Now that number n, let's think about it. If we're going to try and factorize it, well, it's not divisible by any of these prime numbers on our list. It's 1 more than a multiple of 2, so it's not divisible by 2. It's 1 more than a multiple of 3. It's not divisible by 3. It's 1 more than a multiple of every single prime on the list of primes that we have. So this number n is not divisible by any of the primes on our list. So it doesn't have any factors that are primes on our list. So that either means that n itself is prime. That's what is a prime number. It's only divisible by itself and 1. Either it's prime itself, or it's got a prime factor that we didn't know about before. Either way, there's something gone wrong. We found a new prime that wasn't on our allegedly complete list of primes. So at this point, we say, magic word, contradiction. This contradicts our assumption that we made. The assumption that we made can't be right, because we've ended up with something that doesn't make sense. I call this the Sherlock Holmes method of proof. Once you've eliminated the impossible, whatever remains, however improbable, must be the truth. So in fact, our assumption that there's only a finite number of primes led us down the garden path of something that ended up being impossible. We had a complete list of primes, and now we've found a prime that wasn't on our list. So actually, all along, there must have been infinitely many prime numbers. So this is a fantastic idea. You take your life in your hands and say, okay, I think this thing is right, but I'm going to just assume the opposite and see where it takes me. Hopefully I find some, I prove that 1 equals 0, which we know isn't correct. So my initial assumption was wrong, and so the thing I really wanted to prove must be true. The great mathematician G.H. Hardy, there he is looking very severe, he says this is one of the great techniques, one of the finest weapons that we have at our disposal. It's a far finer gambit, he said, than any chess gambit. A chess player may offer the sacrifice of a pawn or even a piece, but a mathematician offers the game. We kind of risk everything to see if our hypothesis is true. So I'm going to show you just one other proof by contradiction. Now we know what the technique is. And again, it's an old proof, but it's just so amazingly ingenious that it's going to make you smile. Makes me smile. Okay, so we're going to prove that the square root of 2 is irrational. So a rational number is one that you can write as a fraction of whole numbers. Something like a over b, where a and b are whole numbers. If you can't do that, then we say the number is irrational. Now, there's when people first started thinking about mathematics and numbers, there was no suspicion that such numbers could exist. But they do, and even in the most sort of commonly occurring places. The square root of 2 is just the length of the diagonal of a square of side 1. We haven't had to delve down the back of the sofa for this thing in some weird esoteric situation. It's really naturally occurring, the square root of 2. You can't avoid it, even in the most basic of geometry. So the idea that this thing can't be written as a fraction is very strange and exciting and exhilarating. But how do we prove it? Again, it's this, how do we know? We can't check all possible fractions. So we've got to use a different argument, and the argument is this proof by contradiction. Let's imagine a world in which actually the square root of 2 is rational. What would that mean? It means we can write it as a fraction. But once you've got a fraction, you can always cancel it down to its lowest form. If there's any common factors on the top and the bottom, you can cancel them. So if there is a fraction that is root 2, we can assume that we've just cancelled it down, cancel any common factors, and so we can be happy that we would be able to write root 2 as some a over b in its lowest form, no common factors in a and b, they're co-prime. All right, so we don't know anything about root 2, so let's square both sides so we don't have to think about that scary thing. If we square both sides, we get that 2 is equal to a squared over b squared. So we can rearrange that. A squared equals 2b squared. Now, at this point, let's think about numbers. A is a whole number, so is b. So the square of a is an even number. Now, if you take an odd number and multiply it by itself, the answer is still odd. Odd times odd equals odd. So a can't be an odd number. It must be an even number. So a is twice some other whole number, c, let's say. Okay, we put that back into what we've got. So 2b squared is equal to a squared. A is 2c. So a squared is 2c all squared, which is 4c squared. And now we've got 2b squared is equal to 4c squared. We can cancel a 2 there and find that b squared is twice c squared. Now this looks a bit familiar because we just sort of had something like that already. B must be an even number because its square is even. The square of an odd number is odd. So b must be even. But, oh, hang on a minute. Didn't we start by saying a and b had no common factors? And now we've proved they're both even. That can't be right. That's impossible. That's a contradiction. Okay, so our initial assumption that root 2 was rational led us to something that obviously false. And so it must be all along that root 2 is irrational. So that's the power of a proof by contradiction. It allows you to deal with cases where there's infinitely many possible things that you would have to check and deal with it in a really efficient way. Wonderful proof technique. All right, so we talked about some lovely proofs. We've talked about making conjecture, and then we have to prove it. But you can't get something for nothing. Every proof relies on either facts you already know are true, like an odd number times an odd number is an odd number, or even further back than that, basic axioms, facts that we don't even try to prove. We say these are sort of truths we hold to be self-evident. An example of this is in geometry, of course, we all learn very early on that the angles in a triangle add up to 180 degrees. The proof of that, or one proof, goes like this. It's very simple. You take your triangle, you draw a line through A parallel to BC. That gives you, so the angles I've marked as green, those are equal because their alternating angles are equal, right? Same with the blue angles, equal because alternating angles are equal. And then we say, well, we know the angles on a straight line add up to 180 degrees. So that means the green plus red plus blue is 180. Those are the angles in my triangle. Done. But the very first thing we said was draw a line through A parallel to BC. That is one formulation of the famous fifth postulate, the parallel postulate of Euclid. It's an axiom that he uses. He says, we're going to begin with these axioms that are just obviously true. There's some discussion as to how obvious that is. But if you remove any of those basic ground rules, I mean, if you remove the parallel postulate, this proof does not work. So you can't even start this proof. So it opens up the possibility for maybe other things can happen if we put ourselves into different geometries. So it's not that this theorem is false or that the proof is false, but really there's an invisible asterisk that says, assuming the axioms of Euclidean geometry, right? If those are our ground rules, then we can prove this. If those are not our ground rules, we get other things that can happen. So if you start looking at the geometry on the surface of a sphere, on a curved surface, you get triangles whose angles can add up to things other than 180 degrees, which is wonderful. You might think, well, there aren't even any straight lines, how can I make a triangle? But we have to think about what a straight line actually is doing for us. What is the kind of philosophical definition of a straight line, if that's not too esoteric? On a plane, between 2 points, the straight line between them is the shortest path between them. So if we take that as really the motivating reason to think about lines, on the surface of a sphere, the shortest path between 2 points, the shortest paths there, are arcs of great circles, like equators. And that's why planes flying long haul will follow those curved paths rather than going in what looks like straight lines on the map. So if you take those as our kind of spherical lines, then you can think about triangles which are bounded by 3 lines. Now, that all sounds like it's going to get extremely complicated and horrible. Spherical geometry sounds scary. But there is one proof, spherical geometry, that is so lovely, it tells us something about triangles that I want to show it to you. And this is what we can do. We are not any longer having to involve the parallel postulate. That is not valid on the surface of a sphere. Okay, so it involves us knowing this shape. So this is a shape you can't really have on a plane. It's the shape bounded by 2 spherical lines. It's called a lune. It's a bit like a crescent moon or something. And there's one that I've highlighted, but actually every pair of lines will create 2 lunes. There's one kind of a shadow lune going round the back that's also created by these 2 lines. So take this lune here. We can work out its area based on the surface area of the sphere. It's very easy. If the angle there is x between the lines, then that same proportion of the total area will be used by the lune. So we don't need to know the formula for the surface area of a sphere. If you do, great. Let's just call it S. Then the area of that loon with that angle is just x 3/60ths of the total surface area, whatever that happens to be. Okay, so now with that in mind, let's imagine a spherical triangle. So that is the region bounded by 3 of these spherical lines. Any pair of those lines defines a loon. Well, actually, 1 loon at the front and 1 loon at the back. So there's my spherical triangle, the blue one, and then I've got 3 loons that are created by the 3 possible pairs, green, red, and yellow. And actually at the back, that whole thing is repeated, sort of antipodally, if that's a word. You've got 3 loons kind of going around to the back, and they all overlap in another copy of that triangle at the back. All right, so we're going to now think about that sphere. The whole surface of the sphere is completely covered by these 6 loons that we've defined. But there's some overlap, so we can't say that the surface area of the sphere is just the sum of the areas of these 6 loons because of the overlapping bits. We've got to take those into account. The triangle at the front there is covered by those 3 loons. So we've counted that 3 times. And the triangle at the back is also covered by the sort of shadow loons at the back. So we've counted that 3 times as well. So we've counted 6 triangle areas instead of actually just 2. So if we take away 4 of those, then everything ought to match up. So what I'm saying is the surface area of the sphere is 2 lots of the red loon, so the red one and its shadow, 2 green loons, green one and its shadow, 2 yellows, and then we take away 4, whatever the area of the triangle is, which we don't need to worry about. And those are equal. Okay, we know how to find the area of a loon. If the angles in the triangle are x, y, and z, then we're going to get x 3/60ths, y 3/60ths, and z 3/60ths. Those are going to be the areas of our loons. So we get this expression, and what we're going to find out is something about the angle sum, x plus y plus z. On the plane, that would be 180 degrees. On the sphere, you can rearrange this, and you find that the angle sum, x plus y plus z, is bigger than 180. It's 180 plus a bit. And the amount by which it exceeds 180 is dependent on the area of the triangle, how much of the surface of the sphere is taken up by this triangle. And that intuitively makes a lot of sense. If you think about a very big triangle, like the one we saw, angles are much bigger than 180. But if you imagine a really small triangle, make it smaller and smaller and smaller and smaller, we're getting closer and closer to the 180. Until in the limit, maybe if you talk about drawing a triangle on a sphere of infinite radius, i.e. a plane, you recover the Euclidean 180 that we all know. So I just love this argument. I think it's so beautifully simple and gives us a fascinating fact about spheres. So we've seen lots of different proofs, and some of these proofs are thousands of years old. Is there anything new under the sun? Well, there's one huge question. There's one huge development, and that is computers. So we can ask ourselves, to finish with, can computers ever do proofs? Can computers prove theorems? And there are sort of 3 parts to this. There are 3 ways in which we might employ computers. The first has been happening for decades already, and that is computer-assisted proofs. Maybe you've got some, most famously the 4-color theorem, if you're familiar with that. You've got some thing you're trying to prove, and maybe you find a way to say, if I could just check these, 200,000 cases, and make sure that it holds in all of these cases, then they would be representative of the whole thing, and I could prove really rigorously that it would work. Everything might be reducible to one of these configurations. And of course, you aren't going to be able to check those cases by hand, but you can program a machine to check them. So that is happening and has been happening for many decades. And I'm thinking, okay, ideally we'd all love a half-page, beautiful, elegant proof, but if we can prove our theorem at all, that's good. So these things, I think they're completely valid. And if you worry, how do you know the computer hasn't made a mistake? Well, how do you know you haven't made a mistake? Do humans make more or fewer mistakes than computers that are correctly programmed? Discuss. I think the chance of a stray neutrino changing the 0 into a 1 and making the computer output be wrong is small and probably smaller than an error in a proof of 200 pages or something, which some mathematical theorems, they are that long or even longer to prove. So that's one, computer-assisted proofs. 2, which is kind of starting to happen, and it's a really interesting area of research, is computer or machine verification of proofs. So a human does a proof, and then you turn it into kind of language that the machine can understand, and it checks the proof for logical consistency. And I think that's very interesting. We have spell checkers, why not proof checkers? The final frontier of this, and we're really in the infancy, is computers, can they find new theorems and prove them without human kind of intervention? And that is, not really happening yet, I would say, but maybe the Gresham professor in 100 years can revisit this question. So, the concept of proof, then, as we've seen, I hope I've convinced you, it's really absolutely vital to mathematics. And it makes mathematics different, really, from other disciplines. In science, what we can do is test our hypotheses really, really stringently. We can never absolutely 100% prove something because something could always turn up and turn over our preconceived ideas. Newton's laws work brilliantly unless you happen to be going almost at the speed of light, and then you need to bring in other possibilities. It doesn't make Newton's laws less good in everyday life, but we know we need to refine our ideas, and that can happen when we are doing science. We test things with experiments. In a court of law, we have to prove things beyond reasonable doubt. And in mathematics, we have to prove things beyond unreasonable doubt. So, I think that's the highest standard of proof. Well, I hope you've enjoyed this and all my lectures in my series. It's been a real honour to serve as the Gresham Professor of Geometry. Thank you very much.
Thank you, Sarah. I think we've just heard the proof of why Sarah is so wonderful. Actually, I've just noted the title of your next book in the middle of all of that. Look, The Incident of the Circle. I think that's going to be
Yes.
a perfect title. Gosh, that's gone now. My questions have gone. I'm going to just get rid of that. Okay, so I'm just going to refine these questions, but in the meantime, are there any questions from the floor? Yes, we have one at the back, in the middle.
Hi, firstly, thanks. Do you have any opinion on whether a ChatGPT-like AI might be useful in finding proofs?
Well, at the moment, if it is like ChatGPT, we have to say no, because they famously hallucinate. And they don't really, the concept of truth is alien to them. They're just pattern spotting or using huge amounts of data gathering based on everything on the internet, and then predicting the next most likely word. And given that I have heard a rumor that not everything on the internet is correct. So I think we can't, those kinds of AI, no. But there are different things that are being developed by mathematicians that are really about making sure every step is completely rigorous. The issue at the moment with machines finding theorems and proving them is that they don't really understand yet what makes a theorem interesting. So they might prove, hey, I can prove that the sum of the numbers from 1 to 10 is, whatever it is, 55. Great, theorem 1. Theorem 2, the sum of the numbers from 1 to 11 is 66. And, you get a bunch of things that are really not very interesting because they're all encompassed by some obviously more general thing that a human looking at it could instantly spot. But the machines are not, as far as I know, really yet able to do that kind of discrimination of what is interesting and different. So you get lots of very dull, boring theorems at the moment. But, we will see.
So at the front, we have one here.
Visual proof is visual proof is a proof. Is a visual proof is a proof.
Is a visual proof a proof? I would say, you've got to be careful. If anyone came to my lecture last time about mathematical illusions, where I proved, didn't really, but appeared to prove that all triangles are isosceles using a diagram that was misleading, then, you do have to be careful. But I would say visual proofs, they can show you the essence of a thing. You may need to just write a couple of lines of algebra to be absolutely certain. But I do not, say down with triangles. I say I love triangles. I love diagrams. Diagrams help us understand. So I would always, sometimes a diagram is just the absolute thing you need to see more clearly, even if you then are writing some algebra afterwards.
So,
there are two conjectures that you and I certainly know. The Goldbach conjecture about the sum of...
yes, every even number greater than 2 can be expressed as the sum of two primes.
And the one that there exists infinite number of prime pairs,
Yes.
Both of which, as far as I know, have not yet been proved. Do you see any fundamental reason for that? Because I think computers have not proved, but demonstrated the proof of
computers have verified, let's say verified, checked both of these conjectures. So, are there infinitely many twin primes? Is every even number expressible as a sum of 2 primes? Computers keep finding twin primes. Computers have checked all the even numbers up to extraordinarily high number that these things appear to be valid. It's highly suggestive of them being valid, but that is not enough, right? That is not enough. And you might say, well, in real life, I've concocted this circle example to make us, think that we can't trust. But surely if you've checked 10 billion cases, it's not going to be wrong. Well, it's probably not going to be wrong, but we haven't proved it yet. Sometimes things do switch over. There's a fun theorem I know about putting... The question is, can you fit, which is better, putting a square peg in a round hole or a round peg in a square hole, right? Which one is the most efficient in terms of taking up a higher proportion of the space? Now, you can answer that question easily. Then, naturally, as a mathematician, you extend it to n dimensions. Which is better, an n-dimensional spherical peg in an n-dimensional cube, or vice versa? There's one answer all the way up to like 9 dimensions, and then it swaps over to be the other way around. And it's a really cool little theorem. I don't know why, it's just really cool. So, that's only 9, but there are examples that go much higher. We can't ever be certain. Are these things fundamentally, they clearly are fundamentally difficult because no one's managed to prove them yet. And some of these things that involve prime numbers, because prime numbers themselves are what you get when you've removed all the patterns, they are just fundamentally difficult to deal with. And so anything that involves prime numbers tends to be difficult. But beyond that, hopefully we will prove these things eventually. I think they're both true.
There's a question right in the far back corner over there, and then one here.
Hello, thank you. The point just mentioned touches on the fact that not all things are provable or disprovable.
Mm-hmm. Yeah.
So we're stuck with that, thanks to Mr. Gödel.
Well, yes, although I'd have to say, so Gödel's incompleteness theorem famously says, if you have a system of kind of abstract logic set up that is sufficiently, let's say, complex to encompass all the things we might want to ask about numbers, and is logically consistent so we can't prove false things, there will be statements that you can make within that system which you cannot prove within that system. That's true, that's a theorem. However, that doesn't mean that maybe there might be not be a different way to think about things that might allow us to prove it. Actually, the proof of this theorem kind of involves a statement which says about itself, in a very loose way, I cannot be proved within the system. And if it can be proved within the system, then it would be false, so that isn't the case. If it can't be proved within the system, then you've got something that is true, because it's correctly said it can't be proved. However, in that, you come out knowing that the statement is true. So it's a bit weird, because you've sort of proved it, but you haven't proved it within that system. So even these sort of putative Gödel-like statements, somehow there might be a way to attack them. So I never lose hope.
Next question, right at the front here.
If
you could just wait for the microphone, please.
Thanks. So proof only is as good as the axioms it rests on, I presume.
Yes.
You've just told us Euclideans have had to say sorry.
Well, they haven't, in the sense that they only ever said, this all follows from these axioms, right? So they were quite Euclidean geometry is very clear from the outset as to what assumptions are being made. Now,
you assumed, you put a lot of faith on the axioms as they did. What do you think constitutes a sound axiom?
Well, that's we can have a whole many weeks of discussion about that. One point of view says, you can do whatever you like. You can define the rules of the game. Right, we're going to play a game. I'm telling you what the rules are. We're now going to play this game. That's the game you've created, and the rules tell you what is possible within that system. So, from that point of view, any axioms you like, as long as everyone knows what they are and you can find the consequences of them. In practice, we don't just pick axioms randomly. We pick axioms that appear to reflect something about the way the world is, or about the way numbers behave. So in my kind of area of algebra called group theory, you have a set and things inside it, and you can combine them, but there are some rules. One of the main rules is, if you combine two things in your set, the answer should be something else in your set. So we know, or we believe that's true, we say that's true of numbers, right? If you add together two whole numbers, the answer is a whole number. That's an axiom of this structure called a group. It works really well because it seems to reflect things that happen in lots of areas of mathematics. You combine symmetries, you get more symmetries. You combine functions, you get more functions. So we tend in practice to use axioms that we find helpful, that give us theories that we can develop that have applications in lots of different areas, or uses in lots of different areas. But once you've defined the axioms, according to whatever methodology you like, then within that you just say, well, subject to these rules, these things are true. And that's pretty impregnable.
Let me just take that back. Thank you. There's one question just by the wall over there. I think that will be the last one we take.
Thank you very much for that. You started the lecture by showing some really old but elegant proofs,
yeah.
And as you pointed out, they gave great insight. Do mathematicians worry with the introduction of computer-based proofs that you might start losing future insight in the way that the elegance was created in the past?
Yeah, so this is potentially an issue that if, the thing I did with the n squared plus n plus 41 of just let's laboriously check through all the things. Now, that's laborious when you do it by hand. Of course, you could get a machine to do it instantaneously, even in Excel or something, and then you can get the same answer. You haven't had to do any work, so maybe it feels like it's just as quick and good. But on a much more bigger scale than that, the fact of it being very, very easy to do difficult, complex calculations, millions of them, it's tempting to do that, and then you don't perhaps get the insight you might have if you were forced to really think about how this fits together and how it's structured. But I would say sometimes those machines are really, really helpful for even helping you to get to a conjecture, because you can just look at a huge number of possibilities and say, oh, look, this seems to be always happening. Then you try and get some intuition and play around with the ideas. So I think we can work together with the machines. We can cooperate for a bright future, and I don't think we're going to need to dispense with human mathematicians just yet.
For the next part of this, I need my glamorous assistant who's going to arrive from the back. Because we can't let you go without a few words of thanks from Gresham College. So let's first bring out our gifts, which is a bunch of flowers, rather looking nicely, from a supermarket near you.
Thank you so much.
Thank you very much. And on this is a fantastic list of people who have been the professors of geometry before you. Robert Hooke, amongst others, who you recognise from the diagram. Yeah. And it's fantastic to see your name at the bottom as the first woman on that list.
Thank you.
We're very proud of you. That's wonderful.
Thank you.
And then you might need a drink to go with it. I'll put that down there. So please, once again, thank Professor Sarah Hart, not only for today, but for an absolutely fantastic series of lectures. And I suspect she may be back. Thank you very much.
Thank you. Thank you.